All right, welcome to Chapter 9, Phase Diagrams. Let's start off by just describing what a phase is. So a phase is just a homogeneous portion of material that has uniform physical and chemical characteristics. All right, so you can have two different phases that have the same chemical makeup as long as they are different physically. So for the example here is just liquid water and solid water. Okay, so ice and liquid. So they're both chemically just pure water, but one is a solid and one is a liquid. So those would be considered two different phases. Or you could have two phases like the one on the right that's got syrup, a water and sugar mixture, and then it's got ice. These are going to be both different chemically as well as physically. All right, and then let's see. So in terms of solutions, when we talk about a liquid solution, that would be like your sugar water, where you've got the sugar mixed in with the water. That's a liquid solution. And if we have a solid solution, then it's the same idea. We're mixing two components together, say. It's forming a solid, but the two are completely mixed and homogeneous throughout. Okay, so up until now, we've only seen solid solutions. So we only had one phase in our materials. The component now, when we talk about phases, phase diagrams, materials, are just the pure elements or compounds that make up the two ends of the phase diagram. So we're going to look at the case of water and sucrose. All right, so let's see what happens if we add sugar to water at 50 degrees Celsius. So first with our phase diagram, we're going to have the composition on the bottom, and it's going to give us the composition of one of the components. So we have to always double check and see what that is. So this is a percent sugar. So 100% sugar means that this is my sugar axis. And then on the left side, we've got 0% sugar. So that would be my water. Okay, so those would mark the two ends of my diagram, my two components then being water and sugar. Okay, so I can start off with pure water. And let's say I start adding in sugar. So maybe at this point, let's see, let's go all the way out to 20. So at this point here, it's a 20, say, weight percent sugar solution. So perhaps I've got 20 grams of sugar and I've got 80 grams of water. So as a weight percent, then that's 20 weight percent sugar. And so I can keep going and I can be adding more and more and more sugar in my water. Okay, so we were at 50, so I'm staying on this 50-degree line. At some point, somewhere in here, I am going to try and add more sugar, but I'm going to end up with my liquid syrup solution plus I'm going to start seeing sugar precipitate out and sit on the bottom of the glass. I can't get any more sugar into this water at this point. I've reached the solubility limit of sugar in water. Right? So over here, I only had a liquid. All right, so I could do that at multiple temperatures, and if I did, I'd find that I get a curve that looks maybe something like this, where as a function of temperature, I'm separating the liquid and the liquid plus sugar regions. Right. So this is referred to as my solubility line, which shows me the maximum amount of sugar I can get into the liquid before I start to precipitate out the sugar. All right, one other thing to notice on this line while we're here is that when I'm on the solubility line, and I'm right on it as I'm adding the sugar in, I still have 100% liquid. It's all liquid. And my composition, let's say, okay, I'll eyeball this. Let's say this is 70% sugar. As I add more and more sugar and I start to move over onto the right side here, and I'm going to try and shift my labeling up here a little bit. As I go ahead and shift over here onto the right side, adding more and more sugar in, we said we're going to get sugar precipitating out because I've saturated my liquid solution. So in other words, no matter where I am at 50 degrees C, the composition of my liquid is always 70%. I can't get any more than that. So as I'm adding more and more sugar, I'm just simply precipitating out more and more of this second phase. So again, this is a two-phase region, liquid plus sugar. So that's going to hold no matter where I am in temperature. I'm just going to have different values of the solubility limit, and the higher in temperature, the higher the solubility limit, the more sugar I can get into the water. Okay, so we're going to come back to this idea when we're dealing with solids. All right, so here's the diagram just as an example for the sugar and water solution, and then here's one for your water and salt solution. Okay, again, showing this idea of the solubility limit. All right, and then if you keep going more negative on this diagram, then you'd start getting into solid phases as well. So here that is for the salt and water solution. The liquid solution is called a brine, and this homogeneous material, the liquid solution, here is a single phase or a solid or a liquid solution. Could also be a solid solution in the case of the solids. This is the homogeneous part. The other part of the phase diagram gives us a mixture of two phases, and that's a heterogeneous material that's got more than one phase in it. So I'm going to try and be careful at using these terms, so I'm only going to refer to these two-phase regions as mixtures, and solutions, that word is reserved for single-phase regions. All right, now in the salt solution case, you can see that I have to get below minus 21 degrees C before I actually start to form ice and salt. Now in this case, this would be ideally 100% water as solid ice, and then 100% salt. And so they would completely separate out. If I can hit this special composition here, then even down to minus 21 degrees, I still have only a liquid, so I don't have any piece of it frozen. If I don't have enough salt, then I'd be over here somewhere, and I'll still have the brine. It won't be completely solid, but I will have some ice mixed in, so I got kind of a slush. And the same if I got too much. So there is this ideal point here that where I can get the lowest temperature with having only liquid. And this is kind of the principle of the way that an ice cream maker works when you're adding salt into the ice water bath that's around your ice cream maker. What you're actually doing is you're absorbing heat out of that ice water bath as the ice in it melts, because of the salt that you've put in, and the temperature of that bath will actually lower. And ideally, you could get down to this sort of minus 20 degree number if you had exactly the right proportions. But you do lower it significantly, and that allows the ice cream to get formed. So previously, we only talked about homogeneous materials or solid solutions, single phase materials. We took a look at a micrograph of, say, an iron carbon alloy, and this was the case for having a very small amount of carbon in the iron. So in this particular case, the carbon weight percent carbon would be less than, so my carbon composition, say, is less than 0.022 weight percent. And we'll see that later as we look at some of the phase diagrams. But if I have a very small amount of carbon, then I have a single phase solid solution. And I have not exceeded the solubility limit, and so we don't precipitate out any sort of carbon phase. So now what we want to do is we want to start looking at heterogeneous mixtures when I've got more than one phase. So I'm going to have at least two phases, two solid phases. All right, so here we're looking at a copper aluminum alloy. And what happens when we exceed the solubility limit of copper in the aluminum? And so when that happens, we'll get a second phase out. When you have two phases now, one of them is going to be more rich in one component and the other is going to be more rich in the other component. So again, in this case, the two components here are aluminum and copper. Okay. The phases that are present is alpha and beta. We give them Greek labels. And in this particular case, if we were to measure the compositions in the alpha and the beta, we would find that the copper, that the beta is aluminum rich, and that the alpha is copper rich. And when we get to the phase diagrams, we'll be able to put actual numbers on these. Right. So all of the boundaries you see in here are now phase boundaries, right? Boundaries between phases. The original grain structure would be on a much larger scale in this case. All right, so with that sort of preliminary, let's go ahead and just show you some examples of phase diagrams. And then next time we'll get into some calculations. All right, so this diagram is called an isomorphous diagram. There is a lot of terminology in this chapter, so you do have to kind of keep yourself a little cheat sheet of the terms, right? But iso meaning same, right? Morphous meaning structure. So this is a diagram that has the same structure for all compositions. So in other words, you can see this is the alpha region, and it doesn't matter. So on this side we have copper. It doesn't matter how much nickel I put into the copper. As I'm walking across the diagram down here, I only have alpha. I never exceed the solubility. There's no solubility limit. And I can do the same and start with nickel, right, and add copper and walk this way on the diagram. And so copper and nickel is one system that's completely miscible. The atoms are about the same size. They're both face-centered cubic, similar electronegativity. So all of these things allow them to form a nice single phase for all compositions. Now, if you heat it up too high, of course, you're going to melt. So there's my liquid. And I've got some fixed points on here. So on the left side of the diagram, we said that's 0% nickel. So that means it's copper. So what I have here is the melting point of pure copper. And then what I have over here then is the melting point of pure nickel. Okay, so those are my two extremes, and you can see now I've got these two lines connecting the two. Now this is interesting because in this region that connects these two single phase regions, I have two phase region. I have a mixture, right? And my mixture contains the two single phase components that are, I shouldn't say components, consist of the two single phase liquid and alpha. And so here I've got my solid plus liquid in this region in between. All right, so what that means is that when you start making alloys, you no longer have a melting point, right? The melting point's defined for the single components, the pure elements, right? I'm either above or below that one temperature value, and I either have a liquid then or a solid. But if I was at, say, 60 weight% nickel, right, so I'm up along this line, if I'm sitting right here at, let's say, 1330 degrees Celsius, I'm sitting right in the middle of an alpha plus liquid region, solid plus liquid region. And that would be my equilibrium amount. I'd have solid, I'd have liquid. And we'll talk about to figure out how much of each I'd have, but it's not going to become any more solid, it's not going to become any more liquid as long as I hold that temperature. If I keep going up in temperature and I exceed this value here at about 1350, then I will have all liquid, so I've completely melted. And if I look at the other way and drop the temperature, as long as I'm below about 1310, then I'd have all solid. Okay. But anywhere in between those two numbers, I'm going to have those two temperature values, I'm going to have a solid plus a liquid. So I have a range now of melting when it comes to alloys. All right, but this is an isomorphous diagram. This is a eutectic diagram. Eutectic. And this eutectic, this word eutectic, it's a Greek word, and it means easily melts. So in the previous diagram, you saw how the melting point changed from one end to the other. Now we'll see that the melting point here that marks the two ends, that's actually higher than where the alloy can become a full liquid and melt. Okay, so this is something unique going on. So this is the melting point. Let's just make sure we got this all marked out of lead. This would be the melting point of tin. Got composition tin on the bottom. I've labeled my two ends. It's real handy to do so that you don't mix up the composition values. But it means that I've got a system that easily melts. And if I'm sitting on exactly 61.9 weight percent tin, and that means then that I've got 38.1 weight percent lead. Okay. Got the right tin here. That's my alloy composition. And so I'm exactly 61.9. At this particular temperature in this diagram, I do have a melting point, okay, for that one particular alloy. That's called the eutectic temperature, okay, based on this eutectic diagram. So at 183 degrees C, if I'm just over that, I'd have all liquid. Just under that, I've got a mixture of two phases, two solid phases, alpha and beta. So again, you're going to see that we always call our solid phases with Greek letters, well, for most of the diagrams. Okay, but if you see a Greek, it always means solid. Now, if I have less than or greater than the 61.9 composition, which is also referred to as the eutectic composition, then I get my range of melting again. So if I'm over here at 30, for example, and I'm heating up my alpha and beta solids, once I cross over 183, I'll be sitting up here in this region, and I'll have alpha and I'll have liquid. So again, I have sort of this slush of solid and liquid, no more beta. And then if I keep going, eventually I'll get to this temperature here where I'm now all liquid, okay, complete melting. Okay. And likewise over here, if I was at a high composition value, I could be over here in this beta plus liquid. Now, on the two ends of this diagram, I actually have single phase solid solution regions. So I have an alpha over here in this region, and on the other side, I've got a beta. Those are my single phase solid solutions. So I can have a certain amount of tin in my lead, right, depending on temperature here as I walk this way, and I were to hit this solubility limit. So this is the solubility limit, just like when I was adding sugar to water. So now I'm adding tin to lead. And if I exceed this value and add a little bit more tin and walk into this region, now I'm going to have alpha fixed there at that composition, And then I'm going to precipitate out this beta phase way over here that is mostly tin with a little bit of lead in it. This is just another eutectic system to show you that all the eutectic systems look the same. General form, this is copper and silver now. You can see now I've got a eutectic temperature, 779, a eutectic composition of 71.9 weight% silver. So let's define a few of these lines. I will try not to use these terms, but it's good to at least know that these are most common terms. If you do hear them, then you can refer back to a slide like this and see what exactly the authors are maybe talking about. The top line, which separates an all liquid region from a region with liquid plus solid, is referred to as the liquidus line. And then likewise, if I have all solid and I'm separating a region again of solid liquid, then this is the solidus line. So solidus separates all solid, liquidus separates all liquid from my solid liquid region. So liquidus, solidus. And then this other line here, which separates all solid from another region with more than one phase, is referred to as the Solvus line. All right, this is copper zinc, so you can see the diagrams get a lot more exciting. Students typically refer to this, well, for a long time as a draft, but lately it's been the brontosaurus. But you can see now as you walk across this diagram, we've got a phase called alpha, and then we're basically just walking through the Greek letters. So we got alpha, beta, gamma, delta in there. We got a little epsilon in here. We got a little eta, all the way over here on the right. So these are all solid phases. They have different compositions, obviously, as you can see, and many of them will have different structures. So along with the phase diagram also comes a couple of pages that would have these listed and would tell you what their structure is. Are these face-centered, body-centered? Are they orthorhombic, tetragonal? It's going to tell you that kind of information. This dotted line means we're not exactly sure where this line is, but somewhere in here. Plus, it's also difficult typically to, when you fall below this line, to get this, what's called beta prime. And the beta prime is an ordered alloy. So all of the alpha, beta, gamma, delta, epsilon, eta are a random mixture substitutional solid solution of copper and zinc. The beta prime is one that would be ordered. There'd be a preference for where the copper and the zinc sat. And you saw that on one of your tests for copper 3 gold, right, where the copper sat in all the face centers of the face-centered cubic cell, and in all the corners sat the gold. And that was an ordered. Otherwise, we could have that same composition of the 75% copper and 25% gold. And if it was completely random, then every location in that face-centered cubic lattice can be thought of as kind of a mixture of the copper and the gold and in those ratios in terms of a probability of what's there. All right. And then we can get some diagrams like this one, which if we kind of look at this for a little bit, we can see that if I was to imagine a line drawn down here, it's like we have two different eutectic systems sort of put together, right? So there's a eutectic here, liquid to two solids, and that's all that eutectic means. The eutectic reaction is a liquid going to a solid 1 plus a solid 2. Okay, that's the definition there of a eutectic reaction. And so over on this other part of the diagram, this is still liquid over here. I have a eutectic point right there, right? That is liquid dropping down into two solids, beta plus Mg2 lead. All right, so it looks like two eutectic diagrams put together, and what's separating them at this one composition here is actually 2 magnesiums to 1 lead. So this is 67% magnesium, 33% lead in terms of an atom fraction, right? Stoichiometry here. In terms of a weight fraction, which is what all our diagrams are going to be in, it's up here more like at 81% lead, since the lead element is so heavy. But this is called an intermetallic, and the intermetallics are ordered, and this is showing the lattice or the unit cell for that particular one. So this looks like the black atoms here, the lead atoms, are on a face-centered cubic type lattice, and so we know that if we count them all, we get 4 if it's face-centered cubic. And it looks like the magnesiums are sitting in these sort of tetrahedral sites. And so these are fully in the cell. So there's 4 on top, 4 on bottom, right? Because there's tetrahedral sites right behind every single corner. So that's 8. Okay, so we said there's 4 lead there in the unit cell, 8 magnesiums. And so you can see that's a 2-to-1 ratio, like the stoichiometry says. All right, and then our important diagram, the iron-carbon system, and this one we'll be looking at in the very last part of this particular chapter. And we'll look at this one in some gory detail. Just point out for now that this is an iron-carbon phase diagram, or sometimes we just referred to this as an iron cementite or iron carbide phase diagram. Because notice it stops at a carbon amount of 6.7 here. The rest of the diagram is not on here. And the reason for that, there's some subtleties in it. I'm going to just hold off telling you why for now, but there is a line that runs down here like this. Okay, so this wasn't an arbitrary cut, and that corresponds to the iron carbide. Okay. So 3 irons and 1 carbon, and that ratio in the unit cell. Okay, so this diagram does stop on this right-handed line. So I was in a particular region, and this region stops on that line, and it stops over here on this line. So we'll look a lot at the iron-carbon phase diagram, like I said again, towards the end. The special point that we'll look at in here, I'll just mention why we're here. You can see here we have a point that looks like a eutectic, except that now we've got a solid, gamma, and when we drop through this point, we get our alpha and our cementite. Sorry, I keep calling it cementite. We'll talk about that later. Iron carbide. And so that's a solid to 2 different solids, and so that's referred to as a eutectoid. We'll keep using this terminology. This diagram also has a eutectic that would be up here, liquid going into 2 solids. So that is my eutectic. All right, well, next time we will go ahead and try and make some calculations on some of these diagrams, and then after that we'll start to look more closely at the eutectic system. And then finally, when we get towards the end of this chapter, we'll come back to this iron carbon and look at this eutectoid reaction. So just to review the terminology, this is just a helpful slide for you. Again, we've got the solid solution. That's our homogeneous region, single phase. The mixture, which is more than 1 phase. The solubility limit, which are these lines here, which are also called the Solvis lines. We've got our components, which are the 2 ends of the diagram. Our phases. So in this particular diagram, that would be our alpha, our beta, and a liquid. Let's see, the solidus line, remember, is this one, all solid from this solid liquid region. The liquidus line is all liquid from this liquid solid region. And then the solvus we just drew in there. Eutectic, meaning easily melts. This is the eutectic composition and the eutectic temperature. And we also looked at an isomorphous system. That example was the copper nickel, where we had one single phase for all compositions, complete miscibility.